I use some rules for the packet checking. It's a good idea to register a protocol which will not be noticed by NDIS hooking firewall. But for existing rootkits, like DeepDoor or Pelegroso, which are going to hook in this open block of a certain protocol binding, it's not possible. They use technique of repatching firewall handlers in this open block structure. This may work for simple firewalls, but advanced ones will check their hooks for presence. So if we patch in this open block directly, some firewalls may detect these hooks, and they may set them back or just inform a user that there's some kind of a rootkit in the system. To leave hooks intact, but to register a rootkit protocol, we may use some passive anti-hooking techniques to be sure that no part of a firewall will be modified. As I mentioned before, the techniques that firewall may use to hook NDs could be either export table based or direct code patch based. As for export table hooks, they may be defeated by finding original API addresses in the ND's image driver. Direct hooks may be defeated with the code pullout technique, which I'm going to discuss later. The first technique used by firewalls is export table hooking. And to find original functions, we may use these methods. First, we load the ND's driver from the disk and map its sections with a custom PE file loader. Then we just walk its export table to find all needed relative virtual addresses and apply found RVAs to the original ND's image. And then the rootkit may call functions directed by a pointer and not relying on any import table anymore, because the import table is hooked. The last thing the rootkit must check is the direct code hooks, because even if the rootkit somehow finds original functions addresses, these functions may be hooked in the ND's image code. So the other solution for overcoming ND's hooking techniques is this. It's possible to use a totally new ND's image so that no code, so that we may be sure that no code will be patched there by a firewall. To do this, we load this image from the disk with ploader like in the previous solution, but we fix all absolute pointers of this image to the existing ND's.sys image, because we want our new hook-free code to use existing ND's data. We're just cloning the code, but we leave data pointers in original state. The advantages of this method is the initialization speed, basically, because it's very simple, so we can perform few operations and it will work pretty fine. And the other advantage is that the loaded code will be always correct, because it's just a simple clone of the running ND's driver. This technique is portable because we don't need to implement some kind of a disassembly engine and PA loader for every processor which current operation system supports is also not needed to be implemented. The disadvantage of this solution is the used code size of the generated image. We are going to use only a few functions, but we load the whole in this driver. And this code is identical to the original disk. And if some kind of memory scanner will check for duplicates of driver's images, it will find that actually there exists two copies of this driver in the memory, which is strange. And now the code pullout engine. It's the more intelligent solution. The idea is to build a sufficient in this code sub-tree. We should fix all absolute pointers to the existing disk image as it was done in the previous solutions. But the main advantage of this solution is that the generated code size is much smaller than the full disk image. Let's say it's about 30 kilobytes of code for these four hooked functions, which I mentioned before. The four functions like in this register protocol, in this open adapter, and two others. When we will generate a code sub-tree, this code may be mutated with any polymorphic algorithm, and this means that all code signatures will be broken. And if some kind of memory scanner will try to detect this copy, it will fail. The disadvantage is that the main disadvantage is that this engine is architecture dependent. For every supported architecture, it's needed to implement a code coverage and rebuilding tool. So I said about advantages and disadvantages, but actually I didn't say anything about the details of this solution. So the next two slides are about the details. To build the code sub-tree, we just need to perform a simple coverage of the code and rebuilding the covered code. To do this, we will just walk our entry points, and original entry points will be defined as relative virtual addresses of the needed APIs. When we will walk them, we will stop on execution transfers, like unpredictable control transfers like jump rec32, or any kind of returns like read, iRead. These types of instructions will mean that we come to the code that has been already analyzed. This will mean that our branches has just ended. And if we come to code that has been already analyzed, we stop our walking and take another branch to analyze. As for calls and conditional jumps, they actually fork execution flow. They add branches to later analysis. A sub-tree coverage map is complete when there is no more branches left in the analysis queue. The final steps of code pullout techniques is to rebuild all generated code to make it be possible to run. We have to recalculate entry points for the addresses which were specified as the top of original code subtrees because the addresses have changed since we are going to move our regions of covered code we should relink all relative jumps and calls in the generated code because they have been broken when we moved all covered regions to the one big piece of code. That's because all relative instructions that connect non-adjacent code blocks were damaged. And the final step of the algorithm is to fix all relocations to the original and this image. After these steps, we will have generated code, which will be much smaller than the whole and this driver, but it's absolutely hook-free because we used original driver image from the disk and not from the memory. Okay, we've discussed a few tricks about bypassing simple firewalls, and then now we'll move to modern ones. These firewalls, in addition to the discussed techniques and new firewalls, we'll check these open blocks structures for code pointers integrity from time to time. And this way, deep door and Pelegrosa rootkits may lose their hooks because they just repatch the original firewall pointers in these structures, like in this open block and this protocol block. Let's see how modern firewalls perform protocol walking. They register a temporary protocol, and this way they get a pointer to that points to somewhere into the list, which is called in this protocol list. But this registered protocol will not actually point to the head of the list. It will not point to the head. The head of the list, which is called in this protocol list, is not exported. And the other thing is that there exists a spin log which protects the list of protocols from synchronization issues, and it's called in this protocol list log. And this log must be acquired when a firewall walks the list, otherwise a race condition may occur. But none of current firewall acquires this log. Furthermore, none of firewalls now searches for the this protocol list head. They just register a temporary protocol. So this solution is not absolutely safe because when